In this particular video, I'm going to explain the necessary criteria and necessary conditions for a function, for a two variable function, to have the maxima and minima, uh, along with one examples associated with this. So here's the definition for any function. Let's suppose that we have any function f of x y of the two variables has a local maxima at a comma b if f a b should be greater than or equal to f x y when it's near a b, then f of a b is called a local maximum value. And similarly, if f of ab is less than f of xy when near to the ab, okay, when it's near ab, then f has a local minimum at ab, and f of ab is a local minimum value. So simply it's very clear. So for any function to have the maximum value at ab, so it should have the highest value in comparison to the nearby other values. Okay, so similarly for the minimum case. The condition required for the maximum and the minimum of the function. So first, actually there are two conditions, or there are two tests. First order derivative test. In case of the first order derivative test, if f of xy has a local maxima or minima at ab, then the first order partial derivative of f exists. Then there is f of x ab should be equal to 0. Here f of x represents actually the partial derivative of the function with respect to x, and fy represents the partial derivative of the function with respect to y. So first of all, what we actually do is we actually make the first order derivative to be 0. We will see later that in the case of the example also. So second order derivative, in case of the second order derivative, we will actually find the value of the d. So where d is f of xx means partial derivative of x, double derivative actually, and with respect to x. So similarly this one. So fyy means partial derivative of y 2 times, similarly others. So there can be many cases like the value of this determinant value. This is actually the determinant. So this determinant should be greater than 0, and f of xx should be greater than 0. So then we say that the function f has the local minima at at ab. So similarly, if d greater than 0 and f of xx less than 0, then f has a local maxima at ab. And similarly, in if d is less than 0, then ab is called the saddle point, and f of ab is not a local maxima or minima. And if d greater than d is equal to 0, then no information about maxima and minima, so further analysis needed. So we actually test from the perspective of these four conditions. So we have given example of the two variable function like this, and we have to find the local maxima or minima and the saddle points of the function. So what we do first, we just find f of x. Fx means partial derivative of the this function with respect to x. We will get this one. Similarly, we will find the partial derivative of y. Partial derivative of y with respect to y, we will get this. We then what we will do, we will just make f of x equal to 0 and f of y equal to 0. So we will get like this. We will actually get the value like this, and this will give actually y is equal to x to the power cube. Putting this value in actually this one, there is another equation y cube minus x is equal to 0. So from first one we actually have y is equal to x cube. So in place of the in this place, in place of the y, we put x cube, and it will become x to the power 9 minus x. So we just take the common, and then we will just do some calculations related to like this, and we will get the values, over here. And actually we make it 0, and we will get the value of x at 0, 1 and minus 1. Then thus these three are the critical points actually, when for x is equal to for when x equal to 0, y equal to also 0, because y is equal to x to the power cube. So that's why we actually get the three critical points. So now for the second order test, for the second order test actually, for the second order test we actually for the second order test we actually okay. So f of x, partial derivative of x with respect to x, f of xy, f of yy, and we will get the value of d like this one. And the value of d for at 0 0 is 16 minus 16. So thus the origin is the saddle point. Okay, origin is the saddle point, and that f does not have the local maxima, because if we look at to the condition, like here, if d less than 0, then that point is represent actually saddle point. So so here this represent the saddle point. F does not have the local maxima or minima at 0 0. Similarly we will test at point 1 comma 1. We will get this one, and f of xx, f of 1 1 is equal to 12 greater than 0. So it implies that at point 1 comma 1 the function has the minimum value. So function has the minimum value. And similarly we can actually test for the this one, another one also. So this is the way by which we actually find the local maxima and the minima of the function. So thank you very much.